So, as I was introduced, my name is Arik Bergman. I'm from the Tel Aviv University, and today I'm going to talk to you about increasing the dynamic range of both Rayleigh-based OFDR, strain temperature interrogation system, and how I'm going to increase this dynamic range using an amplifying add-on module. So, though my advisor opposes giving talk outlines because they carry no information, I still think that I can give you some outline which will carry some information. So I'll give you a short introduction on Rayleigh scattering, its application to sensing, and I will shortly introduce the optical frequency domain reflectometry. Then I'll give some application examples of fiber optic sensors embedded in composite materials, specifically the structural health monitoring applications. The problem we face in this type of application is that OFDR interrogators require minimum amount of reflected light for reliable measurements, and optical loss, such as microbending loss, may severely limit their performance. And of course, the proposed solution, the amplifying add-on model. So briefly on Rayleigh scattering, you all know that if we place the electric sphere in a constant electric field, it will generate an electric dipole which is proportional to its volume and is a function of the electric constant. If placed in an oscillating electric field or electromagnetic field, it will radiate. And if the wavelengths of the radiation, of the illumination, is much larger than the sphere radius, then it will generate the total scattering cross-section, which is proportional to the square of the sphere volume and inversely proportional to the force power of the wavelengths. And of course, you cannot mention Rayleigh scattering and not talk about sky being blue. So this is believed, the Rayleigh scattering is believed to be the reason for the blue color of the sky due to scattering from air molecules in the atmosphere. In a similar manner, many scattering centers exist in the silica fiber, in the core of the silica fiber, due to nanometric fluctuations of the core refractive index, due to density fluctuations of the amorphous silica, and the fluctuations of the material composition of the doping. In total, the Rayleigh scattering comprises some 85% of scattering loss in the fiber, of course, at low intensities level. The backscatter power can be calculated by the simple equation of the product of the incident power, the backscatter capture fraction, the scattering coefficient, and half the pulse length. The capture fraction in the single mode silica fiber is in fact very low. And if we consider the linear attenuation due to Rayleigh scattering of 0.15 dB per kilometer, then we end up with a really small number of -72 dB per meter, which is an excellent for communication, but it's very challenging for sensing. So we are interested in measuring the Rayleigh spectrum at some range in the communication wavelengths. So for each frequency, the total amplitude will be the random phasor sum of all reflectors within this resolution cell. And by this we can acquire this spectral signature, which is fiber unique signature, and it is information rich. Now let's remember what happens when fiber Bragg rating deforms. Well, the normal unstrained fiber Bragg rating has a Bragg reflection wavelength which is proportional to its period. And when it is strained, it is actually, its reflection wavelength shifts, and it shifts linearly with the light strain or the temperature change. So we've previously showed how we acquire the Rayleigh spectrum at some point But now what happens when this point elongates? So we acquire actually the same reflection spectrum, but it will appear shifted in wavelengths. So we can think of this Rayleigh spectrum as a nature-made chaotic Bragg grating. So how we do distributed measurement? We select some section of the fiber and take its signature. And then when heat applied or strain, then we take another signature. Then we correlate those signatures, and this shift in wavelengths will have the same linear relation as in the Bragg grating with strain or temperature. So the most simple, in concept, the most simple system for acquiring this Rayleigh spectrum and making sensing is optical time domain reflectometry. So in coherent optical time domain reflectometry, we scan the frequency step by step, which requires stable laser frequency. Then we shape a pulse, which requires high extinction ratio pulse modulator. And this pulse travels along the fiber, reflected, back to the detector. The spatial resolution is determined by the pulse length, and the distance is derived from the time of flight, of course. Some authors use a reference arm for increasing the signal-to-noise ratio. This, of course, requires a highly coherent source. Alternative method is OTDR, which does not directly measure strain or temperature, but it measures the change in the reflection of the Rayleigh spectrum amplitude, in the Rayleigh reflected amplitude. Of course, some authors use a detection scheme to interfere in different areas of the fiber. Some authors use homodide detection, some use heterodide detection for increasing the SNR. But all these systems basically measure the change in scattered amplitude, and they cannot learn nothing about the strain, but only about the perturbation. So all OTDR systems, they have a trade-off, a principal trade-off between the signal-to-noise ratio and the spatial resolution. So if we are interested in increasing